Hello, let's look at what is computer science. There seems to be a lot of confusion about what it really is. Some people say there is no such thing as computer science, that it is just mathematics or it's an extension of electrical engineering, digital electronics, and so on. Let's first see what we teach in the name of computer science. If you take a typical CS curriculum, it has all of these subjects, there's data structures, operating systems, blah, blah, blah. We teach about 20 to 30 subjects, and together we call this computer science. How does it all come together? What really is computer science? Let's just begin by trying to group or classify these subjects into several categories. First, you have these 6 subjects that you can call the foundation or the core of computer science. There is data structures, algorithms, theory of computation or automata and languages, organization, operating systems, and some form of programming. Everyone would agree that this constitutes the core of computer science. And then we teach a lot of practical courses in terms of scaling things up, improving performance, databases, system software, web technologies and web services, multi-core security, cloud, and what have you. We also teach a lot of tools and technologies in the name of computer science. There are lots of programming languages, there are development tools, software engineering tools, and what have you. And on top of all of this, we teach a number of domain courses about applications, areas in which computers can be applied to do things more intelligently, and so on. How do all of these things fit together? What really is computer science? Let's just compare this to a traditional field of engineering, say mechanical engineering. If you look at mechanical engineering, you have these standard courses there: engineering mechanics, theory of machines, material science, fluid mechanics, thermodynamics, heat transfer, IC engines, and so on. And if you were to look at a product of mechanical engineering, say this product, it's fairly obvious how all these things come together. For example, here is your theory of machines, here is the fluid mechanics, inside there is the IC engine, there is heat transfer happening here, there is material science, and so on. It's very easy to figure out how all these things come together in any product of mechanical engineering. On the other hand, when it comes to, and if that's not good enough, you can always go for an exploded view which tells you how the IC engine works inside, and so on. Traditional engineering has very good ways of doing all this. If you look at the same thing for computer science, right, it's not at all clear how all of these things come together. If you look at a product, a software product, for example, all you see is a cardboard box or a logo. Where is the data structure here? Where is the operating system? How is the algorithm applied in this product? That is not at all clear to us, right? So if you look at this definition of computer science, say in Wikipedia, it says it is about the theoretical foundation of information and computation of practical techniques for algorithmic processes and so on. What is all this? What is a foundation of information, and what is this algorithmic process? Is that the core of computer science? Right? So first of all, why is it called a science? Why is it not computer engineering, or why is it not mechanical science or electrical science? How come we often give an engineering degree in a science called computer science? Are we all crazy? Right? Is this really a science, or is this engineering? Why is it called science? If you look at the science behind traditional branches of engineering, say the science behind mechanical engineering, it's all about physics. It's Newton's laws, gravitation, thermodynamics, and atomic theory, and relativity if you want, and a little bit of chemistry. So the science behind engineering is really physics and chemistry. So also electrical engineering and so on. But what is the science behind computer science? Right? It's not physics, it's not chemistry, it's not biology, and mathematics is not a science. So what is the science behind computer science that tells me why sorting takes n log n, right? Or why are trees more efficient for searching than arrays? Or why can't we do binary search on linked lists? What is the science that gives me these answers? Traditional science does not answer these questions. Computer science seems to be beyond physics, right? If you take sorting out of the present context, and whether you sort heavy objects or light objects, whether you are sorting solids, liquids, colors, or names, and you try to do sorting in outer space or in the Andromeda galaxy, if you wish, or if you do time travel and then do sorting, it should still take n log n. Why is that? Right? What is the science that explains all of this? So here is a definition. In computer science, we have a science of our own. It is not the natural or the traditional sciences. What is it? It is whatever explains computing phenomena which cannot be explained by traditional sciences. That is a definition of computer science. So we have a science of computing. In this science of computing is a model of computing. It has a control unit, a memory unit, a reading head, input, output, and so on. And we make certain fundamental assumptions about this computing model which decides how the computing model behaves, why sorting takes n log n. In addition to this, we might need a model of information, a model of communication, and perhaps even a model of cognition about social sciences and so on. But at the core of all of this is a model of computing, and the behavior of that model is really what computer science is all about. This fundamental model of computing has made some very, very significant assumptions. It says that instruction sets have to be minimalistic. It says that there is going to be a stored table of instructions from which execution takes place. It makes an assumption that memory units are a linear sequence of cells. There is no other organization of memory. There's going to be a single reading head which will read from this memory. There is not going to be any awareness or consciousness for this processor. The processor is not going to have a big picture. The behavior depends only on the current configuration, and so on and so forth. And the consequences of this is what we study in computer science. So the science of computing answers questions about what does it mean to compute, what is computable, what is not computable, how efficient a computing can be, and so on. But it does not always match the way the human brain works. We don't think the same way. We don't communicate the same way. We don't perceive the world the same way. We understand, learn, evolve, and so on differently from computers, because what is computable for us is very different from what is computable for this computing model, right? So there are burning questions here. Why do we need anything other than arrays in data structures? Why do we need dynamic programming and algorithms? Why do the operating systems need paging and memory, virtual memory? If you ask these questions can only be answered based on this fundamental model of computing and its consequences on what is possible, what is not possible, what is efficient, what is not efficient. Similarly, if you ask the common man has a number of questions about computers. How come computers can store all these high definition pictures, but they don't recognize any of us? How come they can be our accountants, but not our personal secretaries? How come they can calculate so accurately, but there are still computer errors, right? How come they store entire dictionary, but don't speak a word of it? Why do we need programming for computers? I don't need to program my car. Why do I need to program my computer, right? How can a computer run a whole hospital or a medical system but can't cure itself of a simple virus, right? How come Google doesn't know the difference between this kind of mouse and that kind of mouse? So these are all questions that we as computer scientists need to answer, and we can only do it if we understand this fundamental model of computing that we have created, which is very different from the cognitive model of how the human brain appears to work, or at least how we behave. The basic difference seems to be in our abilities seems to be between recognition and recall. If you ask me to recognize my high school classmate whom I have not seen in the last 3 decades, I will still be able to recognize him or her. But if you ask me to recall the names of all of my classmates, there is no way I can do that. Computers, on the other hand, recall very easily. They can print out the names of all of my classmates, but they can't recognize any of them. We are designed to recognize. Computers have been designed to recall, not to recognize. Why is this so? Once again, it is based on the model of computing. If the computing model was different, then the consequences would be very different. For example, if it had multi-dimensional memory or associative memory or a processor which was aware of its own processing or a data-centric model, then certainly the consequences of the computing model and the science of computing itself would be very different. But the standard model of computing is what we follow, and computer science is all about figuring out what are the consequences of that. Right? In a computer science curriculum, we are expected to give a complete and connected view of the entire science of computing to our students, like this, well connected South Indian meal that you see on this picture. Instead, if we don't do a good job of it, our students after 4 years might get a view as though they experienced a meal which started with a French onion soup, but it was served with masala papad, and then they got curry rice with Italian dressing, and then maybe pasta primavera with peanut oil and baklava for dessert. That is not a well connected picture. How do we paint a connected picture of all the different subjects in computer science? Let's see an analogy, right? If you take operating systems, this is like the center of all of computing. If this does not work, the hardware and software applications become useless. This is what brings hardware and software to life. So the operating system is really the brain or the central nervous system of computer science. What are data structures? If you don't have data structures, there is no shape to your data. Data structures are what bring shape and structure to the information that we represent. So data structures are the bones or the orthopedics of computer science. What about algorithms? Algorithms tell the different parts of a computer what they need to do. It's the physiology, right? Here is an algorithm for breathing. It says breathe in, breathe out, and do that repeatedly until you die. And that's an algorithm for breathing. And there are in fact better algorithms for breathing. If you look at lamas or yoga, they give you alternative and better algorithms for breathing. So algorithms are the physiology of computing. What is architecture? It's all about the central processing unit, right? It has got these chambers, these valves, and data flows in from here and flows out of there. So it's really the cardiology of computer science. And there is the theory of computation or finite automata and formal languages. This is something that everybody studies but nobody remembers after a few years. It is similar to microbiology that doctors study, and after a few years they don't remember any of it. What about database systems? These are nothing but data structures on steroids. It's all about engineering. It's all about scaling things. And there is software testing. Everyone says this is essential, it's a good thing to do, it identifies problems, but nobody really likes it, right? It's like the pathology of computer science. Pathology is an essential field. It debugs, it finds problems, it suggests remedies, but nobody really likes pathology. What about performance engineering? It's all about taking the fat out and making it lean and mean so that it can perform better. It's really the liposuction or the Botox of computer science. Artificial intelligence, well, it produces wonderfully useless products such as this. Right? And then there is user interface design. It's all about the before and after. It's cosmetic surgery. And there are microcontrollers and other such subjects. Is it really computer science? Well, it's more like dental work or dentistry. And then we have open source software, right? It's the alternative. It's like the alternative medicine. It's like the Ayurveda of computer science. And finally, we also teach freshman programming to our first year students, and that's really the pediatrics of it. I mean, there is more to this analogy than this picture tells you, because to do a good job as a pediatrician, as a teacher for first year programming, one needs to be really good in all of those other subjects. Only then one can be a good pediatrician or a good first year teacher. What about the engineering aspect of it, right? It's all about making things faster, better, robust, scalable, secure, and so on. So there is also a whole engineering aspect to computer science. Are we doing a good job of this? Is this really what we are teaching? Do our graduates know what is the science of computing? Thank you.